These are your 13-1 notes on trigonometric identities. And a trig identity is an equation involving trig functions that is true for all values. So for every angle, this statement would be true for every expression in the equation. And so there's these three basic identities that we're going to talk about. Quotient identities, which implies like a division is happening. Reciprocal identities, which involves like an inverse or a flipping of a fraction. And then Pythagorean identities, which sort of hints and alludes to the fact that it has something to do with the Pythagorean theorem. A couple of these we've already talked about, but I never really mentioned that they're a trig identity. And so the first one would be a quotient identity, that the tangent of any angle can be found by placing the sine of that angle over the cosine of that angle. Now we talked about that a little bit when we studied the unit circle and quadrantals. That's how we got the tangent value, side opposite over side adjacent. And so if that's true for tangent values, then we have another quotient identity that says cotangent is cosine theta over sine theta. So it just flips them, the adjacent over the opposite. So those are your two quotient identities, and this is true for every degree of theta. Reciprocal identities implies that you're going to have an inverse effect or reciprocal. So cosine theta is equivalent to 1 over sine theta, the inverse of sine. And secant, you have the secant theta is equivalent to the inverse of cosine, and cotangent is equivalent to 1 over tangent. And I actually stated that wrong because it's wrong on the sheet that I'm using. It's not cosine here, cosecant. We talked about that sine and cosecant are buddies, secant and cosine are buddies, and cotangent and tangent are buddies. And so if you notice, all the buddies are defined as the inverse of the original three. The inverse of sine, the inverse of cosine, and the inverse of tangent. The Pythagorean identities, there's actually three different relationships involving, you'll see why we call it the Pythagorean theorem. So the first one is written cosine squared theta plus sine squared theta is equal to 1. And I'll explain this whole squared thing. Tangent squared theta plus 1 is equal to secant squared theta. And the last one is cotangent squared theta plus 1 is equal to cosecant squared theta. And so they're all written in the positive. If you notice, the first one has both trig values on the same side, and then they equal 1, where the other ones have a 1 involved, but they're on opposite sides of the equation. And that's just because they want to write it in terms of a positive 1. Everything's plus. We can rearrange those into different forms, and so we'll do that tomorrow. That's what all that extra space is for. We're going to write that in 3 different formations so that you can see it in terms. Right now, the first Pythagorean triple is in terms of 1. That tells you what 1 is equal to. But I would like that to also read what cosine squared is equal to and what sine squared is equal to. And we'll do that for all 3. So we'll do that in class. The squared, what I want to mention with the squared is it means that you are actually squaring the tangent. The tangent itself, or the cosine itself, is being squared. And the reason they put it with the cosine rather than with the angle, when you would see cosine maybe 30 degrees squared, it implies that you're squaring the degree. And we're not trying to square the degree, we're trying to square the cosine. And so you would almost have to use parentheses. So this is what that symbol, by putting the 2 out in front, it sort of alleviates the fact of having to put parentheses around it every single time. Okay, so we're not squaring the angle, we're squaring the cosine of the angle. That's what that squared means. Now I have all these prove it pages because this is part of the process, is proving these things. I'm not going to prove both of them, but I'm going to go through and then we can kind of do the other one in class and kind of talk about it more. So if we have this right triangle, in a generic right triangle, we call this sides A, B, and C. This would be, we need to come up with a theta angle. So if we call this theta, okay, in terms of theta, this would be the side opposite, this would be the side adjacent, and this would be the hypotenuse to theta. And so the tangent of theta would be, and another way we can write this, we could just leave those words. The tangent would be, we could use the sides BC, or we could call this little a. And then the side adjacent we would call little b, and the hypotenuse we could call little c. So when I want to write the tangent of theta, that would be opposite over adjacent. That would be the values little a, side little a, over side little b. And what they're saying is this should be equivalent as if I put sine over cosine. To write the sine value of theta, that would be little a over c, opposite over hypotenuse. And my cosine would be little b over c. So I need to make those two sides equivalent. The one side is pretty easy, a over b. To make that match the other side, I've got this complex fraction. I could show division, or I could actually just multiply both top and bottom by c. So if I multiply both top and bottom by c, whatever I do to the top, I do to the bottom, and I end up with a over b. This is a true statement always. AB is equal to itself. Same thing would happen with cotangent, just in a reverse order. So that's a proof. I didn't use any numbers. I just used like variables to represent numbers, and it worked every time. We could prove these trig values as well. So I'll just do one of them. If I call this theta, again, we got triangle A, B, and C here. And so this would be the side opposite of theta, which is little a. This would be the side adjacent, which we could call little b. And then we've got hypotenuse, which we could label as little c. So if I do the middle one here for secant, remember secant is the hypotenuse c over the adjacent side b. And they're saying that that is equivalent to 1 over cosine, and cosine is b over c. Anytime you have a 1 over something, that is the symbol for inverse. So we could actually just flip that. So it says 1 over a fraction, you can flip it. For instance, if I had 1 over 3/4, that means the inverse of 3/4 is 4/3. It's sort of an understood mathematical computation where you don't have to show work. Another thing we could do is we could actually divide 1 by BC. So the left side stays by itself, and I can rewrite this complex fraction as a division problem instead. 1 divided by BC, which means we would change it to multiplying by the reciprocal, CB, and 1 times CB is equivalent to CB, always. And so the math calculates and says a number equals itself. That's true always. And so I'll leave the other two alone. For the Pythag identities, I'll look at the, we could do the middle one again, or we could do the first one. It really doesn't matter. But if we go ahead and label our triangle like we have been, got an A, B, and C, classic right triangle. This is the side, this is theta. This is my side opposite, which would be little a. Adjacent is little b, and this is the hypotenuse as little c. So if I do cosine squared theta, that is the adjacent b over c, but it's squared. And the sine of theta squared would be a over c squared. And they're saying that that should eventually become 1. So when I square a fraction, that just means multiply by itself. So you square the top, b squared, square the bottom, c squared. Do the same thing, a squared over c squared equals 1. And right now I have 2 fractions with a common denominator that equal 1, but I'd rather not work with fractions. So if I could, I'd like to eliminate those fractions. So if I multiply this whole side by a c squared, and multiply this whole side by c squared. Whatever I do to one side, I can do to the other. That will eliminate my fractions. If I distribute the c squared to the first fraction, they cancel, and it leaves me with b squared. If I multiply the second fraction by c squared, it too eliminates the c squared and gives me an a squared. And now I have it equal to c squared. Now you can sort of see why a squared plus b squared equals c squared has already been proven by Pythag. We don't have to do this. We don't have to prove this because Pythagoras did it for us. And it's a theorem. It's already been proven. So when you get the two sides of a right triangle, added up, their sides squared, and it equals the hypotenuse squared, that's always true. And so what you'll get with all three of these Pythagorean identities is some form of the Pythagorean theorem. So that proof led us into another theorem that's already been proven. Okay, but we won't have to do that ever again. That just sort of is the proof why these things work for every number, and I'm required to do that. So what we're going to do is we're going to actually use those connections, all of those identities, to help us solve more of like trig values in terms of more of like an algebraic approach to solving these things. So let's break these down. The first problem, they want us to find tangent theta. So treat tangent theta like your variable. You're not going to write x, but just think of it as that's the missing value. And then they're giving us some other value. I have this relationship here, and so I need to use just that one clue. The other clue that they give us is where we're located. So let's just talk about this crazy thing because it's scary, but it shouldn't be. What they're telling us there is that the angle theta is somewhere between 180 degrees and 270 degrees. They're telling you how big angle theta is. And so if you actually were to put that on a coordinate plane, you got 90, 180, 270, and 360. Basically, what they're telling us is that theta is in the third quadrant. That's all. That it's somewhere in the third quadrant. And when they tell us that it's in the third quadrant, we can now apply. All students take calculus. So we can do that right away. We're going to find tangent. Tangent is positive in the third quadrant, so I know that it's going to be a positive value. So whether you do it in the beginning or you do it at the very end, just make sure that you do it. So we use the end part of our clue to tell us that after we're all said and done, we should be getting a tangent that's positive. So now what we have to do is we have to use our trig value identities, and we use them as a formula. So we first look for, is there a formula that involves tangent and secant? So I look at the quotients, and tangent and secant aren't there. I look at the reciprocal identities, tangent and secant are not there. But when I look at the Pythagorean identities, I see a formula I can use. So that's what I want you to write down. I see a formula that involves tangent and secant. So the very first thing I'm going to do is write down that formula. So tangent squared theta plus 1 is equal to secant squared theta. Now we have a formula. And we know the value of secant theta is -2, so we're going to replace the secant theta with -2, since I know its value. The unknown value is the tangent. Now, Pythag identities are always squared, so we need to keep that in mind that eventually we'll have to square things or take the square root of things to get rid of that. Because they didn't ask us to find tangent squared theta, they only asked us to find tangent. So now I'm going to substitute, just like I would in any other equation. I have a value. I'm going to replace secant theta with -2, but I'm going to remember to square it. So the secant is -2, but I'm going to square it now. So I'm going to put that in there first. Tangent squared theta plus 1 is equal to 4. When you square a negative, it becomes positive. And now we're going to solve for tangent theta. I'm going to subtract 1 from both sides. Tangent squared theta is equal to 3. And then to undo the square, I'm going to take the square root. The square and the square root cancel. And so tangent theta is equivalent to the square root of 3. And there's our answer. And it's going to be positive because it's in the actual third quadrant. Now, if you remember from chapter 12, tangent square root of 3 is actually the tangent value of a 60-degree angle. It's a 60-degree angle in the third quadrant. This is a 240-degree angle. You wouldn't know that necessarily, but that's what they're saying. That theta is 240 degrees, and we just found the tangent of it. Now, they're not all that easy, but I do like the algebra that's involved here. So you find the equation, the formula, you substitute, and you solve. It's pretty simple that way. However, the clues get a little trickier. So let's try another one here. The sine, we want to find sine. So this is what we're trying to find. This is my variable. And then they're giving us this relationship to work with. So I'm going to look for a direct connection between sine and cosine. If you look in the beginning, the quotient identity does have sine and cosine, but it involves tangent as well. We don't have a tangent, so we'd have too many unknowns. We do not want to use quotient identities. When you look at reciprocals, there's no reciprocal function that has sine and cosine. So again, we're with the Pythagorean identities. So I'm going to write down the identity we're using, cosine squared theta plus sine squared theta is equal to 1. I have cosine as a half, so I'm going to substitute 1/2 squared plus sine theta is equal to 1. When I square a half, I square the top, I square the bottom. Okay, I'm going to subtract 1/4 from 1 whole, which is easy because what I basically do is change that 1 whole into the fraction symbol and turn it into a 4/4, because that's what 1 whole is in terms of fourths. So sine, oops, I dropped my squared somewhere. Sine squared theta is equal to 3/4, because when you have 1/4 taken away from 4/4, you're left with 3/4. Take the square root. Sine of theta is the square root of 3 over the square root of 4. Whenever you take the square root of fraction, you need to break it apart and then simplify square root of 3 over 2. Now I got to look at my cast, and if we go all the way back to the beginning, they're telling us that theta is in the fourth quadrant, because here's 270 degrees, here's 360 degrees, and theta is in the fourth quadrant. All students take calculus tells me that cosine is positive, but sine would be negative. Since we're finding sine, I need to make it a negative value. Negative root 3 over 2. All right. For cosecant and cosine, cosecant with cosine, there is no direct relationship. I go through all of the trig functions, and I realize there is no direct relationship. So then we have to look at their buddies. So if I can find a relationship with their buddies, then I can work through and find the buddy, and then I can find the other number. So we don't want to go to each buddy. We just want to change one of them. So I'm going to look at the sine of theta instead of cosecant. Is there a relationship between sine and cosine? And there is. So if I can find sine, I know there's a relationship between sine and cosecant. So this just is a little bit longer process. So the first thing I'm going to find is sine, using sine squared theta plus cosine squared theta equals 1. I'm going to replace cosine with 2/3. Sine squared theta plus 2/3 squared equals 1. I'm going to square 2/3. Sine squared theta plus 4/9, don't forget to square the bottom, equals 1. I'm going to subtract 4/9 from 1. When you subtract 4/9 from 9/9, this is 9/9 now. 9/9 take away 4/9 is 5/9. We're almost there. Take the square root. Sine theta is equal to the square root of 5 over 3. However, that's not what we're looking for. They didn't ask us to find the sine. They asked us to find cosecant. But now that I have sine, I have a relationship where I could use sine to find cosecant. So now I'm going to use a different trig identity. And this one is cosecant theta is equal to 1 over sine theta. You have to write down the original identity in its original form. Now we substitute. I'm going to take this sine value and plug it in for sine. So cosecant theta is equal to 1 over the square root of 5 over 3. Now, I told you in the beginning of the notes that anytime you have 1 over something, it's the inverse of. So we don't have to really show any work here unless you want to. The inverse of the square root of 5 over 3 is 3 over the square root of 5. You just flip it. Can't leave it like that because we can never leave these like that. So we're going to multiply both top and bottom by the square root of 5. And I end up getting 3 root 5 over 5. So cosecant theta is equal to 3 root 5 over 5. We got to look at our sign. We are between 90 and 270. Well, that's not really a good clue. So actually, though, if we're finding, let's change that to 180.
We have Madison Oliver and Ariana Desereau to the office.
Let's actually change that so that it reads 180. I think that's just a typo. So if it's 180, between 90 and 180, theta's in the second quadrant. All students take calculus. Sine is positive there, so cosecant would be positive there. So we are finished. And there are your trig values. Now, it's a little bit difficult. There's one more step where you'd have to compare reciprocal or buddy with buddy. So here's kind of the process you look for. Is there just a direct relationship between the two functions? If there is, great, go with it. That is one equation. But what if I had to take the function of one and the reciprocal of the other? Okay, that would mean that you're going to have two different equations and two different identities. And then there's the option of perhaps flipping back the one that you looked at the reciprocal and looking at the other reciprocal. So I keep changing. Maybe it's the first one's reciprocal and the original function. That would still be two identities. And then the long ones would be reciprocal with reciprocal. That's going to be three different identities. So this would require one ID. These two require two IDs. And this would require three IDs. They're a little bit longer, but then you at least know ahead of time. You write them as formulas, you substitute, and then you solve. So good luck. What trig value is equivalent to cosine over sine? And then find the exact value of that particular approach. So try to go through the entire process.